Okay, in this tutorial, we have built the tower. So I'm going to load up a tower that I built previously, which was... this one, 24 tower concept, which has all the cross members like complete in it. So we continued the task of doing the diagonal members, and we did it all the way up the tower. So now we are going to make some simulations. I already have simulations here, but I'm just going to hide those for now, because we don't want to use these simulations. So when you are doing your design, you should be in the design space. When you're finished and ready to do your simulations, you can press save. But even before we do that, there's some information we can find out about our tower. Our tower, for the most part, should all be one body. Well, yeah, because the cap and the box were the other parts, but the box of our tower will be one body. We can already find some information. We can right click and we can go to properties. And what this does is it gives us some information about our tower. We know our tower has an area, which is surface area. That's not super relevant for us. But our object does have a mass and it does have a volume. Now, it also says here that it's assuming that our object is made out of steel. So the mass isn't really super relevant, but the volume is relevant because we know the volume, if we can find like the density of our wood, we can find out what the approximate weight of our tower should be. Now you should know the density of your wood because you all got your 8 pieces. Did you get your wood yet? Okay, the other class got theirs. I can give it to you this lesson. No, next lesson probably. But when you get your pieces of wood, let me just move over here. This is a bunch of wood that someone in the other class forgot, so I stole it off them. But over here you're going to get, and I'm deciding I'm going to give you 8 pieces of wood. So you get 8 pieces of wood. You get to get these pieces of wood, you get to weigh them, and you get to measure them. So you know your block of wood, because you get this measurement, this over here is basically one big rectangular prism. You can find the volume of this wood. Once you find the volume and you have the mass, you can find the density. Because density is mass over volume. And so you can do that calculation. You know your density, and then in your design here, you can find out what your volume is, so you can approximate what your weight is. This is good for when you're doing your evaluation, because if you know how much your tower should weigh, and then when you finish your tower is going to end up weighing more. Why would that be? Why would your tower end up weighing more than the calculation you have here?
Because of like glue that you...
Yeah, glue, yeah. In theory, if you actually put extra wood or less wood, you'll change that number slightly. But what you're definitely adding is the glue. So then you can find out how much the weight of all your glue was. Also, if you had like sticky tape that you didn't take off because sometimes it glues, it gets stuck to the wood. But all that extra stuff we can find out, and you can add that in your evaluation. You can say, if my tower weighed 27 grams, according to the theory, but it was actually 30 grams, you can say, therefore, I have 3 grams of glue in my tower. That's a piece of information we can find here, which isn't using the simulation tab, but we are using Fusion 360 to help us do some calculations. So in theory, that does count as a simulation. But let's find some actual simulations here. Now, I believe I've already shown in class, but I may as well show again for the video. When we have a simulation, we have our design, we save, we go to simulation. If we've run a simulation, actually I think I'll show us running the simulation, and then I'll repeat what I said previously about getting that information from there. So when we start it, you are going to be presented with this screen because you're not going to have any simulations loaded up in your task. We are going to do static stress. Static stress means we're calculating the stress assuming stuff doesn't change angles. And for the very small amount of testing we're doing until our thing fails, it doesn't actually change angles that much. So static first, and it's also the fastest simulation. So it's good to get your first concept ideas and really understanding what's actually happening with our tower. Where is our force moving? So we'll go to static stress and we will create study. And so we have a new study made here now, study 3. I obviously have study 1 and 2 from doing this previously. You should have nothing, so you'll be starting from study 1. Study 1 static stress, and you can also name that if you want to like do different scenarios. First thing before you start, if your object is not all connected, like if you have 2 pieces of timber that are next to each other and you decided to make it as a new object, you're going to have to connect everything together. So the first thing I like to do is over here on the contacts, to press the automatic contacts button. And what this does is it says, anytime there's a piece of a material that's 0.1 millimeter, because that's I consider to 0.1 millimeter. Anytime there's a material that's 0.1 millimeter to another material, let's assume that's a contact and that's connected together. And basically it's going to say it's glued together, which is basically what your tower is. Your tower is gluing 2 pieces together. So we'll press generate, and in my one there's no contacts, but in yours there might be contacts. So it's a good fail-safe to do. Material, now we have it set to steel, and all we have to do is just remember that we have it set to steel. But why each of these studies have different materials is we might, if this is a real world, you might be making an object out of steel or brass or aluminium, say if it's something for a car or a chair, and you change it, you can do the different analyses with that. We have to start setting up this job, so we're going to set up with constraints. Constraints and loads. These are the 2 things we're going to use. So we'll do constraints, and we're going to start by doing structural constraint. This is saying we have to say where this object is not going to move. Because we're doing a simulation, it's calculating it for all values. And if we don't lock it down in position, it's going to say there's infinite many solutions. Like if I have this remote that I'm holding up in my hands, right? Sorry, people watching the stream. If I have this remote holding up in my hands, what is a correct solution for this remote? If I don't attach it to the ground, right, all these solutions in visible space are valid. So it's going to have infinite solutions. I can't solve it. I have to say the remote has to be attached to the ground for me to do like calculations on it. So when we do our structural analysis, when we do our constraints, we're going to pick the fixed one and the target. Now the best targets to do is all the bottom surfaces. Right, so I'm lucky with mine. If I can just hover over it, I can press this, and this whole surface is one face, and I'm locking it up in the X, Y, and Z. So it's not moving in the X, Y, and Z. So the base plate of my tower is not moving. It's very simple. We're trying to simplify it, and that's the most simple way to do it. And then if we press OK, you should confirm this is correct, because there should be a padlock. See how there's a little padlock icon over here? That padlock icon means that that is a constraint. Next, we've got to put a load on our tower. So we're going to go to load, and our load is going to be a force, and we're going to select the target. We, just like we put the constraints, we're going to select the target of the force to be this top, the top part of the tower over here. So this is going to be force pushing down on this part of the tower. Now we've got to pick the Newton value. So this is where we have a bit of a problem, right? I'm going to load up Google. So, oh, sorry, it's my YouTube channel saying that we need to reach more subscribers. How awkward. Over here. So we need to find out where our simulation is steel, but we're balsa wood. So do we remember what unit we use to describe strength for a material? So our first lessons. So pascals is the unit, but what the word I'm looking for is, go on, give me the guy's name, please. Oh, The word we're looking for is Young's modulus. Young's modulus, so Young's modulus is the unit we use to describe strength, and it's measured in pascals. If I Google Young's modulus of steel, it's between 190 and 215. Right, so that's how strong steel is by Mr. Young, who did that test to find that out. So let's do the same thing. Young's modulus of balsa wood is here in Young's balsa wood in pascals. So there we go. Young's modulus for balsa wood is 9 gigapascals. Yes. Balsa wood is measured in 9 gigapascals. What does that mean? We don't really need to know. All we need to know is the relative strength. If balsa wood is 9 gigapascals and steel is, let's just round it off. Let's say it's at 200 gigapascals, right? So that means we can find the ratio of how much stronger steel is than balsa wood. Because if steel is 200 and balsa wood is 9, we can then go over here and say 200 divided by 9, 22 times. Steel is 22 times stronger than balsa wood. Let's just go one up. Let's just say, let's round it up because why not? 23 times stronger than balsa wood. Because let's assume that we don't have that's probably the most ideal pieces of balsa wood. Ours are probably not that ideal. Because it's also going to change depending on if you have... When I gave my students the 8 pieces of balsa wood, I got them to weigh each piece. Some of them are lighter than the others. The heavier the balsa wood, the more fibers that are inside it, which means it's got more strength. The lighter the piece of balsa wood, the less fiber, the more air that's inside it. So you do those are going to be weaker. So if we assume 23, that means our balsa wood is 23 times weaker than steel. So when we're putting our force in, if we put a force value that's 23 times higher than what we want, we can get an approximate for how our material will work. So we're going to put 23. Now, what load did I say you had to achieve to get an A? 60. 60 kilograms, but I need that in newtons. What's that in newtons? It's not 60 newtons. 600 newtons, yes. Because I know everyone's going to screech, but yes, we assume gravity is 10. So 23 times 600, that's our force value we're putting in there. If we press enter, and if we look at this load case over here, load, if we press the edit button, we should see 13800 newtons. That's how much newtons we're putting in to this simulation. And then we press OK. So now, Fusion, before it can do the simulation, it needs to make what's called a mesh. And what we're doing here is we are simplifying the atomic structure of the entire object by making it like one big skeleton. And then Fusion gets those hundreds and thousands of elements and does like a big simultaneous equation with them. So first we have to make the mesh. If we go to mesh, if we go this mesh button down here, if we right click this and we press generate mesh, right, Fusion's going to make a mesh. Okay, and if I press this button over here for toggle mesh, hold on, I'll zoom in, it's actually there, but see now, do you see these faint lines? If I actually hide, I think I can hide it. Can you see those faint lines that are on the steel? Those are, that's basically its skeleton now. So instead of it being one solid object, it's like it's a whole bunch of pieces of like, it's a big truss analysis basically, what's happening here. A big truss analysis. I don't think, can I hide this to make us... Here we go. No, can't show it. All right, sorry. I can't show just the mesh. All right, but now we have everything, and to prove it, we'll go to our pre-check over here. If we press our pre-check, it's going to check that we got all the required things to possibly get it. Doesn't mean we will get a good result out, but we have the bare minimum, right? We've done our mesh, we've done our constraints, we've done our load, everything has a material. There's no parts that are not connected, so we can get a solution. So what we're going to do is we're going to press the solve, and we're just solving, I'm just solving study number 3. When you do it, you'll do study number 1. This study will solve one study, and if I press solve, because my account's on education, it's going to cost me 0. If I press solve one study, it's going to start solving. And I am going to pause the tutorial here, and I'll return back once this thing is completed its thing. And the time that we did this was 1:50, so we'll see how long something like this will take. While it's doing this simulation, you can do something else. In fact, you can even close it. You can even close this and close Fusion. So you can do, if you're doing like homework, you can go to another subject for half an hour, come back. If you do it at the end of night, do your simulation, go to bed, wake up tomorrow. Fusion will send you the updates next time you load it up, and you'll get the results. You don't have to keep the computer on because it's sending it to the cloud computers to solve it for you. Okay, so we're back, and this one only took 2 minutes. This was a quick one. If we close, now over here we see, that's not a good, that's a bit of a problem we see here. So, yes. We're seeing some issues. Some things are going to fail. Over here we have factor of safety. Factor of safety is basically saying how much of that material's structural limits are you reaching. 1 means it's going to break. Less than 1 means it's already broken. If you had like 2, that means your material's only using half of the strength of that material. So as we see here, a lot of the components are going to break. Now, but this part over here at the top, that we see a lot of breakage, this isn't actually a good interpretation of what's happening. Because if you imagine force, it's like evenly spreading that force along the top, but our scenario, we're actually getting a flat plate, so it's also kind of distributing the load. It's not going to bend in the middle. But I'll show you a way that we can actually bypass that and get a more realistic result. But for our first test, if we ignore this top piece, the next part of buckling is over here, I think. So this part over here is going to fail. In fact, anything that's red is less than 1. So anything over here, this is where the balsa wood might fail if we're doing 60 kilograms. We're approximating it because, again, steel to balsa, even though the percentage, even though it's 23 times stronger, it's still not an exact science because we have to include like glue and direction of the grains and all stuff like that. But over here, we can at least predict where our tower is probably going to fail. This one over here, I wouldn't really count this because this is more caused by this part over here twisting it, I suspect, and as I do my next test, we're going to find a way to fix that. So I suspect this over here is where the tower is actually going to fail. This part over here, that's a lot of stress. The balsa wood is probably going to snap there. So let's try and do the next one. Also what I want to do, factor of safety, displacement, we can see how much it moves. Over here, the balsa wood has moved down 70.7 millimeters. And what I want to do is I want to find out how much. I want to find out exactly how much this top part has moved as we put the stress on it. And I can inspect it by pressing this probe over here. And I can hover my probe over here and I can see this part of the tower has moved in the Y direction. This part of the thing has moved down 0.2 millimeters. So as we're doing it, it's moved down 0.2 millimeters. So I'll remember that for my next test. All right, finished results, cool. So we're going to do another study now. We'll do the same study, but this time, instead of putting a force value on there, I want to do actually what our tower is doing. What's happening as we spin the thread on the tower on our testing device? What's physically happening to our tower? Does anybody remember me describing the tower? As I spun the thread, what's actually happening to the tower? It's not force. Yeah, it's actually squeezing. So it's actually doing a displacement. As we're turning the wheel, we're saying, crush this tower 10 millimeters, 20 millimeters. We're doing actually a displacement. So we can do that in Fusion as well. We can go to static stress. We can do another create study. Now again, this is study 4. For you, it's going to be study 2. We already saw that in my one contact, so you do your contacts again, materials fine. Constraints. Well, the first constraint is the same. The bottom, we're going to do the bottom constraint. We're going to press here is locked in. For the second one, we're going to put another constraint. Under constraints, structural constraint, we're going to change it from fixed. We're going to do prescribed displacement. Prescribed displacement. So what I'm saying is in this simulation, this face or whatever one I'm selecting, it's going to move this amount. So I'm going to press this part over here at the top of the tower. And then I'm going to say it's going to move down in the Y direction. It's going to move down 1 centimeter, which is what, 10 millimeters? I'm going to say it's going to move down 10 centimeters. And it's going to do that simulation. It's going to say, what happens in the simulation if you move this face down? 10 millimeters. Everything else should be the same. We're putting no loads in this case, because instead we're doing the prescribed displacement. Now let's go to solve. Everything else should be fine. And we'll go to solve this study. And I'll pause it. All right, so we've done this test now. Uh-oh, this looks bad. Everything over here, factor of safety, wall. That's fine. For this test, we're not really looking for the factor of safety. What we're actually looking at is, oh, it's all red. That's fine. What we're actually going to do is try to find which area has the most factor of safety issues. So we can actually drag this down. And what it's going to do is it's going to hide. It's going to hide the areas. So these areas over here have the most factor of safety, which, the least factor of safety, which means this is the part of the tower that is most likely to break. This kind of makes sense. We've already described in class that all the vertical members, but only notice how it's just a little bit on this and a little bit on this, but a lot in this middle one, right? Factor of safety isn't super relevant for what we want. Instead, because a lot of it's red, because we saw in the original simulation, 0.2 of a millimeter was how much the top actually buckled, and I forced it to be 10 millimeters. That's fine. So I forced it to be 200 times more than the test we did before. But where it's useful, if I go to stress, we can see which parts are under the most stress. And again, I'm going to hide the blue, the bottom parts, because again, we don't really need those. So the area that's under the most stress is this corner over here, is experiencing the most stress. It's experiencing 14882 megapascals. 1.442 megapascals. Now, this is something that doesn't have to scale, because it doesn't matter whether this megapascals is too much for our steel or not, because we just know that this is, so if that's in megapascals, gigapascals is 14 gigapascals, and we know that based on our balsa wood, 14 gigapascals is more than our balsa wood can handle. What could our balsa wood handle? 9, right? So we experience this part is going to fail before that, right? But that's fine. We don't really care about how it's going to fail, but what that means is when we change our design, shh, boys, please. When we change our design, right, you're going to make a new file and you're going to do that simulation. And if you do that simulation and you find out that based under the same conditions, that joint or the maximum stress was 10 gigapascals, that tower will last longer because it's 10. And then later if you do another one that's 8, even better, your tower might even survive that amount. Based on that criteria. Also what we can do, we can go to reaction force. We can find out what the reaction force is. So over here, this says those top pieces of the tower are, if we were to push it down 1 centimeter, our steel tower, that's the equivalent of 60 kilonewtons of force. Right? Is that Oh, I can hover this. Okay, so the amount of force going in the y direction is 60 kilonewtons. And we said that 600 is what we needed, right? But now we are dealing with steel. So if steel was 60,000 and steel is 22 times stronger than balsa, we can divide that number. If we divide that number by 23, we can say how much force our balsa wood tower would be experiencing if it were to buckle 10 millimeters. That's the most iffy part. You could use that maybe in your evaluations and we can go into more detail. The last one, the last test we're going to do, the last one I'm going to show you how to do the buckling test. So study, new study. This one we're going to go to structural buckling. Because remember, anything under compression is likely to fail by buckling. Same thing before, we're going to do our constraints over here. That one's fully loaded. Now for our buckling, we have to put in our force value. So like before, we're going to get our load. And this one, we do have to do our 600 times 23. Okay. So we are limited with this bottom part over here isn't going to be great, but whatever, we have to try it. Is there anything else we can fix? I was trying to think. We might be able to, constraints, we might be able to press, this is all one surface. I think if I press this button over here, it's going to try to stop it from twisting. No, we'll deal with that later. I'll adjust that later. So we just put that force going down. We do our simulation. We solve. We'll come back once that solving is done. All right, this simple thing was only 2 minutes. The time that this tutorial takes is drastically based on the amount of mesh elements that are inside there. So as you increase the mesh count, you get more accuracy, but things take longer. So when we do this analysis, we have here, it says these are going to buckle. This is the area. I mean, how buckling analysis works is it does it until it will buckle, right? But it's saying this is the area that is likely to buckle. These parts over here. And if we go over here, it says buckling. It says the buckling will happen at 5 times the load. So the value that we put in, into our tower, which is supposed to be an A value, it says here according to buckling, it should buckle 5 times higher than that, which is good news for us. It means our thing shouldn't buckle, but one of the problems is this is a simulation that assumes this is all one solid piece of aluminium. Or sorry, steel. Even if we increase the, we compare the strength value, what we're not comparing is that we are not one solid piece of wood, are we? How are we joining our pieces of wood? Glue. And so each of those are going to be a point of weakness. So it's still useful to know that the largest members are the parts that are going to most likely buckle. So when we change our design, we might want all our members to be roughly the same size, especially those vertical members, because they're the parts that are most likely to buckle if it is to buckle. And that also means the reason why the 5 times as much, do you remember we did the critical buckling equation in class? Do we do that on the board? No? Okay. When we do our buckling, it really depends on the end components. And if they're connected very tightly, it's going to buckle a lot. It's going to need a lot more force to buckle. But with our balsa wood, since we've glued it, the glue is kind of a weak point. As soon as the glue starts to fail, it will start to buckle. That's all we need from these tutorials so far. So, thank you. Let me stop.